Okay, thanks, Jim. Again, it's a pleasure to moderate this session. As Jim mentioned, that the National Academies is very interested in this topic. In fact, the Board on Agriculture and Natural Resources is planning a study on this particular topic. So anyway, a new circular economy. So to lead that off is George Post from Arizona State University, and he's going to be talking about accomplishments and challenges. George?
Chuck, thank you. I've got to come off of the mute.
I got you all.
So good morning, everyone. So thanks to everyone who's already made the introductory comments. I think there'll probably be redundancies throughout the entire meeting, but that's certainly an important dimension. So Guru gave me the unenviable task of trying to at least create a framework. Are my slides coming up okay for everyone?
Yes, they're there.
Okay, good. Thank you. So in this first block, I'm going to focus on the issues of the accomplishments and challenges. So obviously summarizing a lot very quickly. I think if one reflects on the past 120 years, we have a major impressive gains in productivity, abundance, and affordability that reflect a number of themes starting in 1900 with mechanization onwards, and a secondary element of that was the reduction in child labor. From the 1970s onwards, the Borlagian Green Revolution in plant breeding, matched also by advances in animal breeding. Biotechnology then gained momentum in the 1990s onwards, and now in the last decade we are entering the era of digital ag. Another very important component in this, of course, for the safety of the food supply, regulatory standards have been dramatically enhanced, impacting quality, safety, labeling, and environmental protection. And this has already been mentioned, at least from this slide, is much a US or G7 nation-centric situation. We have an extremely sophisticated supply chain from farm to fork that relies upon a lot of advanced technologies. But perhaps the most important thing is that we can actually track assets across the entire supply chain. Also within the accomplishments, and certainly now, as we're going to hear later, technology convergence between the life sciences, engineering, and computing is now a permanent feature of all aspects of contemporary science, but certainly with relevance to agriculture, the growth of digital ag through extensive sensor networks and geospatial mapping, a whole repertoire of technologies that stem from automation. Synthetic biology and gene editing is now gaining at an impressive pace. And we also have new biomimetic approaches to alternative meat through synthetic biology and so forth. And perhaps one could argue that data is the new cash crop, at least for the high income countries, where one has then got to have systems capable of managing big data and applying sophisticated machine learning and artificial analytics. But with it comes new risks in terms of the protection of those data sets and their utilization under the broad title of cyber biosecurity. And it remains to be seen where blockchain will actually enter this pantheon of technologies, but certainly many people are exploring new business models and contracts and supply chain methodologies based upon this technology. The next two slides I'm going to hurry by, not only because we lost time, but I was given the fact that these slides are going to be published by the Academy. I'm not going to dwell on it because many of the points have been made, namely the accomplishments I referred to a moment ago are largely a US-centric or G7 nation-centric. And now we have to face the gross iniquities that exist with regard to the fact that many low-income countries do not enjoy the same food security that we enjoy here in the US and the high-income countries. So I'm going to skip this slide and the next slide and go to a point that's already made, that we are dealing with a systems of systems approach. If the overall goals in food and ag are productivity and improved equity in access to the benefits of food, agriculture, and nutrition, it also imposes the need for a global stewardship of finite resource. But as already been made, this is a very complex systems of systems in which food and agriculture are then linked to each of those major systems, which in turn have got hierarchical subsystems beneath them. One Health, I think, merits particular attention because it is the evolving concept of the interdependence of human health, animal health, and ecosystem health. But I think an important perspective when we talk about investment is the fact that the USDA, the overall investment that they're able to make is less than 5% of what the National Institutes of Health is able to invest. So I think that that's an important issue of underinvestment. But I'm not going to belabor the other circles there because they will actually come up. So essentially, if we look at them as food and ag then as a complex adaptive systems comprising multiple interacting systems, as has already been said, there's an extraordinary diversity of stakeholders across multiple domains, multiple sectors, and it's global, national and international. And if our attainable goals are to achieve suitable scale for sustainability and to achieve equity and security, and the broad strategic drivers shown at the bottom, only some of them going from right to left, One Health, but urbanization is a critical factor here, particularly urbanization in lower income countries, because that in turn not only increases food demand, but doesn't necessarily be matched by productivity. And we've talked about digital ag, but much, of course, can be defined within markets, technology, the levels of investment and regulation. But at the same time, we have supranational political policies which are being propagated for the Sustainable Development Goals and the climate treaty, which may be completely unattainable in the current framework. So if we were to look at the characteristics of a complex adaptive system, stating the obvious to many on this call, we're dealing with systems which by definition are nonlinear. They are dynamic and they are interaction, not only within a system, but because of the systems of systems. So we have to consider who are the interactive agents in any given domain? What are their connectivities? What is the robustness of that network of connectivities? And at the same time, we're dealing with systems not only of complexity, but also enormous spatial temporal scale, ranging from the subcellular all the way through to global ecosystems. And like any other complex system, it is subject to disruption, giving rise to emergence, to entirely new state shifts and adaptation. And shown in red is that all too often, because of our lack of understanding of these complex interplays, we have unintended consequences. As has already been mentioned, COVID-19 revealed not only in stark relief the complexity and inadequacies of the American healthcare system, it also revealed many elements of vulnerabilities in the food chain. And as shown there, 54 million Americans, 18 million children experiencing uncertainty. And we saw, again, choke points in the supply chain, reflecting essentially the same sort of thing we're now seeing in chip production, being a constrained issue because of the number of consolidated nodes. And at the same time, the very working conditions within many of the meat packing plants gave rise to excess infections and deaths. So again, trying to meet Guru's challenge as to how we look at this very complex food and ag system, if we are to achieve in the yellow boxes scale and equity, be responsible in our utilization of resources, Then we, of course, have to deal with, on the right-hand side there, population growth. We need to have a 70% increase in food production to meet population projections by 2050. We're dealing with many non-renewable resources, urbanization, degradation through soil, water, infection and infestation, waste reduction, climate change and energy, each of which could be a symposium in their own right. And then going across to the left-hand side, we have the disparities between high, middle and low income countries, the triad, the ugly triad of poverty, hunger and impaired health in the low income countries, and then all the issues that then follow, which are needed in relation to education to achieve equity, ability to access supply chains, impact of trade policies, geopolitics, conflict and national security. So indeed, it is a very complex system of systems. So if you look at where we stand in dealing with this, we essentially, I characterize it as complexity is ignored, not unique to food and ag, where I spend most of my time in healthcare. This slide would apply equally. We're dealing with fragmented linear reductionist concepts, policies and investments, as opposed to trying to embrace an understanding, albeit daunting, of the holistic systems-based strategies, because going to the red box in the triangle, we are now facing escalating complexities and vulnerabilities. Economic, and we've already talked about ecological, emerging infectious diseases as epitomized by COVID, but by no means unique. COVID-19 only being the last of a number of emerging infectious diseases which have hit us over the past 20 years, most of which are zoonotic, moving from animals to people. Supply chain consolidation may very well meet the requirements of business schools for a friction-free economy, but also creates vulnerabilities when those consolidated nodes are under siege. As we move into a big data arena, soft targets emerge for not only those of adversarial mindset, but also the resiliency of those. The issue of equity, we will be facing significant humanitarian crises as a result of shortages in food supply in the coming years, which will also then compound geopolitical complexities, which may very well also overflow into military conflicts and the omnipresent nature of existential threats. So in summary, the food and ag sector, in common with public health and healthcare, are a classic complex adaptive system involving multiple interactive CAS subsystems, a system of systems has already been pointed out. So my principal issue, which I'm sure will come up throughout the day, is that without a far more sophisticated systems approach to public policy, which by definition must be supranational, and a critical reassessment of where we set our R&D investment priorities, both in the public and private sector, we will continue to propagate a patchwork of siloed components, both within the luxury of the US and the G7, yet alone the global population. And we will therefore persist in propagating systems that won't achieve the required global resiliency and equity. And current propagation of reductionist, linear and silo policies will simply continue to amplify risk, vulnerabilities and disparities, which sadly, I think must give rise to a prognostic environment in which escalating socioeconomic stresses, humanitarian crises will lead to geopolitical instabilities and resources, aka the resource wars. Again, with a superficial surf across a very large landscape of systems, I hope, Chuck, it meets the needs to at least set the framework, not only for this block, but for the rest of the meeting. Thank you very much.
Thank you, George. That was an excellent introduction. We probably need communication systems added to your systems within systems. So thanks, excellent presentation to set the stage. Next up to respond his perspective is Jamie Hyman from John Deere. And I guess go ahead and you're all set up, Jamie, thanks.
Thanks, Chuck. Can you confirm you can see the slides?
Yep, you're good.
Perfect. Good morning, good afternoon, good evening, everyone, and thanks to the Academy for the opportunity to talk to this group today about mechanization, automation, and robotics in modern agriculture. So I'm going to start by just setting the stage, and George actually did a pretty good job of this, so I'll be brief. You know, the challenge in global agriculture, the grand challenge is no different today, I would argue, than it was or has been in the past. It's fundamentally figuring out how to do more with less. And that efficiency challenge is increasing, but it's always been there. I would tell you that, you know, the numbers that George highlighted, 10 billion people in 2050 relative to the 7.8 or 7.9 billion people on the planet today, producing a need for 70% more food is a challenge relative to doing that on existing arable land or less arable land in the future, fewer resources going into the production of that food. Also, fewer resources on the labor side. So if you're familiar with the latest US Census data, it's interestingly enough fairly representative of global trends as well. We're continuing to see a population decline from rural inhabitants to urban inhabitants. That produces obviously a labor shortage within the agricultural production systems. And you know, in the last 10 years in the US, that's a reduction of about 3%, 3.5% in the population of people that are available to be deployed into the agricultural sector. In addition to that, farmers are continuing to deal with climate change. It's the single biggest variable in their operations today and is becoming more significant with time in different parts of the world for obvious reasons. So this is the challenge that we're up against, and I would offer to this group that while technology may not be the only answer to the challenge, it is in fact, I think, a significant part of how globally we answer this challenge. So before we talk about the technology a little bit, I want to just maybe rewind for the last 100 years of agriculture. From a mechanization perspective, the industry has been nearly myopically focused on making machines, equipment bigger and faster. They've done that in part because of the labor shortages and the trends in population movement across the globe. In order to make the bushels produced per person more effective, more efficient. But we've reached a tipping point, and I would argue that tipping point was probably in the last decade, maybe two, where becoming bigger and faster was no longer sufficient, and we'd sort of reached a saturation point where the benefits that accrued to bigger and faster were disproportionate with our ability to continue to create bigger and faster machines for global agriculture. And so the shift that's happened has been towards looking at other technology as a means to improve that efficiency in agriculture. And I just point out that in the last 20 years, there's three technology vectors, I think, that have come into play that have made the current state of agriculture extremely interesting and compelling. And in terms of the shift that's happened from a machinery and equipment perspective. Those three vectors are connectivity. Nearly every large agricultural machine today that's put into use is connected in some way, shape, or form. You can think of it as an IoT device. In the case of the sprayer that's shown on the slide in front of you, connected not only with satellite guidance, but also connected through terrestrial cell networks to a cloud infrastructure to support both data uptake and download onto the piece of equipment. So we're becoming much more connected as a fleet, and I think that speaks to the system of systems idea, which I'll talk about a little bit later. But connectivity is sort of a foundational technology that's enabled some of the changes that we're seeing today. In addition to that, that connectivity has produced a rich amount of data, more data today than we have ever had, which lends itself to the opportunity to use advanced algorithms like machine learning, reinforcement learning, et cetera, based upon data sets that traditionally have not existed. in this space. And so that's a very compelling change that's happened, that's made the machines smarter over time and made the decision-making process for the grower much more informed. The last vector that's happened is really the trend and the onward march of an improvement in onboard compute capability, or soon potentially edge compute capability. And that's enabled us to take actions on machines that we have not been able to execute in the past, simply because we suffered from a lack of capability to do the math on the product and to do it in a sufficient time period for it to be useful and actionable in the field. So we pivoted from bigger and faster to, I would argue, smarter over time. That's driving towards a goal, at least within Deere, as we talk about it, towards plant level management. So this idea that we're no longer going to treat every plant in the field uniformly, but we're going to treat them as a master gardener would, if we had a master gardener capable of operating at scale across global agriculture. I think that's a compelling vision because it conjures up this idea that we can be much more precise, and I know we'll talk about precision ag later, but much more precise in the application of crop care, protectants and nutrients, et cetera, water to the plants individually, as opposed to treating everything within a given area in the same way. So let's talk about a couple examples of how that technology is in action. This is actually in production today. This is a product we call See and Spray Select. It is a sprayer that is intended to spray fallow ground and apply a pre-emergent herbicide onto the ground, fallowed ground, that only identifies weeds. So we no longer broadcast spray a herbicide across the complete field, but we actually spray only where the weeds are. And so that has the benefit of reducing herbicide application by 77%. It's significant in the field trials that we've run. It's a significant improvement, obviously, in the ecological impact that a grower might have within their field from that crop protectant application. You can sort of let your mind wander with this technology. It's based upon a vision system on this sprayer boom, in this case, and graphical processing units that are processing image data in near real time. You can let your mind wander once you have that image data. What else could you do? You can forecast that towards things like fungicide application no longer being broadcast, but also being prescriptive. You can also start to think about nutrient application, nitrogen application, as being applied only to those crops that need it, and in the amount that they need it, based upon the color saturation of the images for those specific crops. So it gives you the ability fairly quickly to start forecasting significant improvements in how we treat the input side of global crop production. Talk a little bit about some of the other technologies that are either in the market or coming into the market and are impacting mechanization. I'm going to start with in-field data sharing, and I thought it was interesting that Al mentioned the aircraft fleet earlier from a system of systems perspective. Our analogy to that is this combine fleet in the upper left corner, and for similar reasons, we view it as a system of systems as well. If we can share data within the field from one machine to another, imagine those 3 combines, for example, we can quickly start to think about opportunities to share things like settings between those machines. So if one of them is outperforming another in terms of grain loss, we would want to make sure that all 3 of those machines have access to that information, and so that all of their settings are set to the appropriate or optimal setting to minimize grain loss. You can also start to think about things like logistics services. So when the combine is full and it needs to be offloaded into the grain cart that's behind that tractor, if the combine has to wait in the field for the tractor to show up, that's downtime. It's an inefficiency in the system. It's fuel being used that is not going in directly into producing the grain. And so if you can share the data of what the level of grain is within that combine to the tractor operator, you can manage the logistics in field much more efficiently and much more accurately. Talk also a little bit about remote access. So COVID-19 has actually been an interesting study in field management within agriculture. So we have long had the opportunity for growers to remote into their machines and look to see what's going on. But the uptake in technology associated with COVID with respect to that has been significant. We've seen a lot more interest and a lot more usage of remotely monitoring machines, remotely configuring machines, and remotely tuning machines within the agricultural system, in part because of COVID. That's not going to go away. That uptake in technology is persistent, and we're going to see more interest in the ability to do that. It also helps to solve our labor dilemma in some respect, because it gives us the ability to multiply the capability of one person to help optimize the systems across multiple pieces of equipment. And the last one I'll talk about on this slide in the interest of time is data in the cloud. So we like to think of growers having, in the northern hemisphere anyway, 40 opportunities in their lifetime to run a design of experiments to maximize, the productivity of their farm while minimizing the inputs that they have to apply. And this is part of digital ag. The ability for them to take their productivity data, to take their agronomic data throughout the production steps in any given year, and to understand the causality of their decisions that they've made on the productivity, on the input side of their business, so that they can make better decisions in the next year, is immensely powerful. And so farmers they have that data now at their fingertips, and the analytics capability associated with the rich data sets is driving them to have much better insights into how to maximize and improve their ability to produce the food that we all need. I'm going to wrap up with this last slide, and it's really this onwards march from automation towards further autonomy. We have long had, for the better part of 2 decades, an increase in automation happening within modern agricultural equipment. It started with GPS guidance 20-some years ago to the point now where tractors and combines largely are capable of operating by themselves in the field. That's helped in terms of managing the labor shortages that I talked about earlier. But the final step here is really to get to a point where the automation is sophisticated enough that we can transition to an operator-less machine. And that future is nearer, I think, than some do. I'm paid to be optimistic, so I take that view on it. But the fact is that within agriculture in particular, we have been marching towards this end goal of full autonomy for a very long time. And much of the capability is already built into the modern agricultural machines to get to that point, with this sort of last step of being able to replicate the perception of the human in the cab in order to make the machines fully autonomous. And that's sort of the end state. It gives us the opportunity to separate, for the first time, machine and labor. Those two have always had to come together, meaning that if you had a machine but you didn't have the labor to operate, nothing happened. In this case, when you get to full autonomy, the labor and the machine are one. Where the machine is, the work can continue to move forward. And with that, I think I'll end, Chuck, and we can pass it on to the next presentation. Thanks.
Okay, thanks, Jamie. All right, well, we'll go ahead and move to the next presentation by Neil Gutterman from Radical Grow. He's going to talk about the role of biotechnology in the current existing systems. So, Neil.
All right. Good morning, good afternoon, evening, everyone. Can you see my slide, Chuck?
Good. Yes, Neil. Yeah, Gutterson. Sorry. Yeah.
Gutterson. Yeah, sure enough. Thank you. Well, thanks for the invitation to spend some time with you today and share some perspectives on biotechnology impacting improved sustainability and resilience of global food and ag systems. And I won't spend time on the challenges. They've been well covered, but they are numerous indeed, despite, as Jim pointed out, the successes as well that we have had in our food systems. So I'm going to jump right in. And I want to just start by sort of setting the table, metaphorically at least, so that everyone recognizes the different ways that biotechnology is contributing and can contribute in the future to improved food systems. Whoops, let's see, sorry about that. Let's go back. Why is it not doing that? Shoot. Hold on one second. There we go. Okay, so and in some cases, obviously, the products themselves are, have the footprint of biotechnology, like a GMO. And in some cases, they look the same as any other crops we've had for generations now, but they come through advanced molecular breeding. And so we have three different categories, at least, that I would argue: advanced molecular breeding, biotech traits, the GMOs, and then in the future, genome edited products. There's only one example today of an edited product that's actually commercial in an oilseed crop in the US. I'm showing here sort of a crop and microbe perspective, which I think are the most compelling opportunities. Clearly, the opportunity for biotech to impact animal agriculture, livestock is real. The potential is meaningful, but it looks much more complex, and so and with much more limited impact in terms of GMOs and potentially gene-edited products. And so I haven't highlighted that here. And again, just for clarity, the symbols I've used suggest both past current state as well as potential. The tools of biotech are incredibly robust, and the new ones and genome-edited products give us incredible latitude and ability to design systems going forward. But in fact, just to highlight that the main limitations in the deployment of biotechnology to address the systems that we need to address in the future are about biological knowledge and much less about the technology. So we continue to need investment in the fundamentals of pathways and processes and metabolism, et cetera, that become then the components of building the models for these adaptive systems, which, starting from the very bottom of molecular level, are truly systems of systems all the way up to the supply chains that we've heard about. Now, ultimately, this is going to be about design. And I just want to point out that when it comes to molecular breeding, where biotech is important, most of the design goes into designing the system for breeding, or designing the population of environments in which the desired products are actually selected. So the products themselves are selected, not designed, but the systems for doing that process are designed. In the case of genome editing, and I'm sure we'll have more discussion about this, it actually is possible, I think, to design the actual changes one wants to make, and then the testing is really more about validation than selection. And I think this theme of designing varieties along with the design of new and improved systems is going to be an important one in terms of biotechnology, but also importantly where biotechnology, big data, machinery all come together. So let's take a look at the past for a moment. This is a slide from GMO Answers, which is a site run by the CropLife International. And you can see the set of crops and the associated traits that are commercial in the US. And you can see, with a quick look, that there's only, 10, 2, 4, 6, 8, 11 crops basically have been engineered and are in the food system. Of a much, much larger number of crops. So first of all, takeaway, there's relatively limited application of a really important technology at the end state in terms of GMO products. You can see that also relatively limited number of traits: insect resistance, herbicide tolerance, disease resistance are the primary ones that we see. And the great bulk of acreage comes through some of the major crops, corn, soybean, canola, cotton, et cetera. So applications are relatively limited. However, this has been an economic success for farmers. It has contributed to the current efficiency of our food systems, and also contributed to more sustainable cropping systems, where herbicide tolerance in particular has been pointed at no-till agriculture to reduce greenhouse gas and do a better job of preserving soil health. A long way to come in that challenge. And in fact, there are challenges of the technology which relate as much to the cropping systems that are used in management practices than to the technology itself. We know that overuse of certain herbicides has led to herbicide-resistant weeds that have to be addressed by developing additional herbicides. And so there are some lessons to be taken here in terms of cropping systems and management practices for the future. But with that framework in mind, let's look forward. And what I'm sharing here is a slide courtesy of Kevin Pixley, a colleague at the CGIAR from CIMMYT. I serve on the CGIAR governing board. And this is a nice picture, now taking a bit of a global look at opportunities for this international organization that serves smallholder farmers around the world, some 500 million smallholder farmers across the planet. And you can see that while nothing is commercial yet, there are quite a few traits across quite a few crops, and some that weren't on the prior list, like cassava and banana. Some sort of orphan crops, you might say, and that are really important crops in other parts of the world. So I wanted to bring this, global perspective on opportunities, and along with the fact that if one were to go to the USDA website, you would find sort of similar types of traits and disease resistance and quality improvements and durability that I think are just the beginning of what can be done with genome editing, where we can actually design in the products of the future based on biological knowledge. So that's just a little perspective of what's out there, what's coming. I want to then show a quick slide in terms of this idea of design and systems and how biotech can play a role here. This is a slide courtesy of Charlie Messina from Corteva Agriscience, where I previously served as CTO. And it's about an example of implementing circularity and improved sustainability. And this is a no-till double cropping example where the goals are to minimize waste, keep materials in use, and again, have reduced tillage impacts on soil. And so, looking to the south in the US, question is, what are the opportunities to double crop? And you can see a couple of panels there that show environmental conditions, temperature, rainfall throughout the year. And bottom line is that there's an opportunity within that framework to build cropping system models where we can see both corn and soybean used together in the same growing season. And the ultimate outcome is a much improved use of land. And you can see the example here. So of harvest and planting at the same time. And the important point is that we can now begin to contemplate designing crops to fit into this designed cropping system. And so just to wrap up then, Chuck, just with a final slide that gives a little perspective of the fact that the capital markets see a lot of opportunity with these technologies. And just a few examples here from controlled environment agriculture companies where, much more sustainable recycling and reuse of crops, editing companies, et cetera. So this is real use of biotech in the future for advanced breeding and ways to support improved systems is coming for sure. So thank you. Back to you, Chuck.
Great. Can folks see the presentation?
Yes.
Yes. Great. Good morning, good afternoon, good evening as well. And thanks so much from me also to the organizers for the invitation. My name is Melissa, and I am the Senior Vice President of Freshwater and Food at WWF US, based in Washington, DC. For those that don't know WWF, we're a leading conservation organization globally, and we really have a shared mission. We have over 100 offices worldwide, and we have a shared mission to see people and nature thrive. People really know us from the iconic logo, but really our work is around ecosystems, landscapes, and thriving people in those landscapes. And then I just also wanted to mention, I actually graduated with an environmental science degree from an ag and bioengineering department, at least it was at the time, at Cornell as my undergrad. So it's a real pleasure to come full circle to speak to you decades later about environment and food systems, but to a bunch of engineers. And with only 8 minutes, my intention is to cover a few key takeaways, not at all to be comprehensive from the conservation perspective, and then to really plant some seeds for a few big ideas of the types of innovations needed from what we think about as system scale change needed for agriculture. So the first takeaway that I really wanted to share and leave with this audience is that we do need to bend the curve, not only to reduce greenhouse gas emissions and achieve a 1.5 degree climate future, which I think we all really know is imperative, but we also need to bend the curve on the loss of nature. Biodiversity is fundamental to the health and well-being of life on Earth, but the evidence is unequivocal that we're destroying nature at a rate unprecedented in history. So WWF for several decades has led a global effort to track the status of biodiversity on the Earth Our most recent Living Planet report, which comes out every 2 years, shows that the trends are consistently dire. Since 1970, we've seen a massive decline of wildlife populations globally, and there's a disproportionately higher decline in freshwater species. Basically, this is a planet in peril of losing the diversity of life on Earth that sustains ecosystems and nature, and ultimately all of us. So there's a lot going on in this slide, but the primary point here is that there are 5 major drivers of biodiversity decline, which we also explore in the Living Planet report. But by far the biggest one that I want to point out is land use change, which really includes habitat loss, habitat degradation, and conversion. And this includes both landscapes and seascapes. So land use change by far is the biggest driver of biodiversity loss in all regions of the world. So the openers really did set the scene, and I'll breeze through this pretty quickly, but there's a lot of evidence now showing what the major drivers and impacts are of agricultural production and food systems, both again on climate and nature. We know that ag is the primary consumer of land and water resources on the globe. Food production, as others have noted, is a huge driver of greenhouse gas emissions and biodiversity loss. Again, primarily due to habitat and land use change and habitat conversion and degradation, global deforestation included. And that there's also this real interesting set of calculations, as others noted, the true cost of food, but really the externality costs to society, environmental, but also health and well-being is estimated now at over 11 trillion, even more than the Rockefeller study cited earlier. And then we know there's also this negative feedback loop to agriculture and humans when nature is lost. So for instance, the loss of pollinators has been well documented, and recent studies are really showing that many crop species are experiencing pollinator limitations, which is impacting yield and productivity. And this will only be exacerbated under climate change, which could really put yield stability and food security at risk in the future. And then the last thing I'll mention, of course, at the top of this slide is that we still see 10% of the global population going hungry, and over a quarter now the population really obese or overweight. And with 40% of the food not even going into consumers' mouths and feeding people, it's a really glaring missed opportunity and a loss of precious natural resources, nutrition, and potential. So it's no wonder that there's so much discussion about transforming the broken food system. So here are 3 just general ideas, and I know we're short on time, so I'll breeze through them. One, I just wanted to seed with this audience the idea of performance-based metrics and tools to really drive behavior change and incentives, especially for producers, but really not only for producers. So this is really an example coming out of an innovative public-private partnership from the Nature Conservancy, the Conservation Technology Information Center, and Regrow, which is a private sector company. And they're using remote sensing satellite imagery to map and track changes in adoption of conservation agricultural practices, in this case, cover crops and conservation tillage in the US Midwest. And so these, but that's not enough, right? So it's great that they are looking, we have less than 5% adoption, for instance, of cover crops, and maybe 40 to 50% of adoption of conservation tillage. But those are practices, and we really need to drive performance-based metrics and tools to look at impact, at least even estimating impact and performance in the landscape. So they're also coupling this OptiTill information system model with a denitrification decomposition model, the DNDC model, to estimate changes in soil organic carbon as well as nitrous oxide emissions. So again, using this to look at what is the long-term impact of adoption, and then how do you drive incentives and behavior change to get more uptake. And so this is really being used now in public-private markets and mechanisms, and how do we align and have a pre-competitive approach to this so we don't have a zillion systems out there. And then, we've got carbon voluntary markets and ecosystem service markets that's coming online. It gets valuated into land prices. And then there's a lot of influence right now on the finance sector, including impact investors, risk mitigation management measures, as well as even access to finance itself. So building these performance metrics and tools, performance-based metrics and tools that really drive overall reduction in GHG emissions should be the priority. I know there's a lot of interest in carbon sequestration and the potential for ag, but I really want to reiterate that we need to look first and foremost at mitigation and reducing the footprint of ag. And that actually means largely tracking not carbon, but nitrogen dynamics on the field, crop inputs, animal production, and manure, but nitrogen is the key. So that brings me to another really innovative tool and partnership led by private sector, academics, nonprofits, foundations, and government researchers. And you may have seen earlier this year that Carbon Mapper was, which is a nonprofit, launched with its partners a new satellite program to really help improve the understanding and accelerate the reduction of point sources of methane and carbon dioxide emissions. And so it's targeting the energy and oil and industries, gas and oil industries, but it has applications, as you can see in the photo on the left, to large dairy operations or animal production facilities. And so the innovation here is really timely data and transparent data that is of adequate spatial resolution to allow for actionable science-based decision-making. And also the oversight and accountability to track and monitor and regulate over time. So methane sat from EDF is another similar objective. And then again, the idea is that performance-based metrics are really critical. But as noted in the beginning, land use change is actually the biggest driver. So in addition to driving efficiencies and sources of field point measures, we also really need to look at the boundary conditions in a landscape. And one of the biggest things is to halt agricultural expansion. So I'm going to breeze through this. I see you, Chuck, that we also really want to look at expansion of agriculture to places that we don't want it. And so again, using satellite imagery, this is an example in the Peruvian rainforest of really verifying operations that have, from a cacao plantation, that have really driven deforestation in what was previously primary forest. And then through, coupled it with analysis, they can really track, this is NDVI and LiDAR analysis, track the carbon losses that have been experienced as a result of this conversion. And so this isn't just the rainforest. I want to mention that in the northern Great Plains in the US, conversion is happening at rates akin to the Amazon rainforest deforestation. And so there's a lot of driving of crop expansion into native grasslands, which are a huge carbon sink, even in North America. And then let me go on to traceability.
We need to move on.
Yeah, so I just wanted to really mention that innovations, as others have noted, in understanding sourcing, sustainable sourcing of food is critical to verifying what, where this is coming, where food is coming from. So it's a $20 billion market, food traceability market is forecasted for that. And that, one of the things that, this is just a quick example, is that, it's not just traceability for food safety, which that is critical, but it is also for our sustainability and human rights and labor and social justice issues. So without visibility and credible assurances, it's impossible to handle these concerns, whether it's food safety, legality, sustainability claims. And this is what consumers, investors, regulators, and the popular media want to know: where is food coming from? So thinking of the innovations for that are critical. There's blockchain. We have an open source True Trace app. There's also things like elemental profiling, which allows sourcing the origin of crops based on their elemental signature. And that we need this for all commodities, not just for shrimp. And they're very complicated, and thinking of the systems to be stood up across stakeholders, across continents, and across across commodities. And the last thing I'll just mention, and I'm finishing up, Chuck.
We really need to go.
Yeah, I know. Is but I as an NGO that works on conservation, this is hot off the presses a couple days ago. I'd be really remiss in not also thinking of drawing the boundaries of the system to nature and the landscape of where ag systems fit. And so we just released this report on really scaling up and out what nature-based solutions look like. And there's a really great case study for agriculture in there. But we really need to think of how to take an ecosystem approach in green infrastructure, ecological engineering, when we are looking at how it can be complementary to gray and built infrastructure as well. So let me stop there. And I know we have one more speaker before we were to do the Q&A.
Okay. All right. Thanks, Melissa. All right. We need to move on to Greg Chikaris, and he's going to talk about the socioeconomic components. And Greg's from University of North Carolina, Chapel Hill. Go ahead, Greg.
Thanks, Chuck. I'm assuming everybody can see my slides. I'm going to give me the high sign otherwise. So I'm Greg Chikaris. Thank you to Chuck for the introduction and for to the organizers for the invitation today. I'm going to talk a little bit about managing the uncertainty in a critical agricultural input, that being water. Water availability is a function of three interlinked systems: the natural system, which governs the timing and location of precip and stream flow; the engineered system of reservoirs and conveyance that alleviates some of the temporal and spatial variability that come about from the natural cycle; and then the economic and financial systems that govern water allocation, things like water markets, as well as financial tools like crop insurance that limit the impact of water scarcity. So I'll make a couple comments within the context of a project on which I serve as PI. This was funded by NSF's Innovations at the Nexus of Food, Energy, Water Systems, the INFEWS program. We had a really talented group of hydrologists, engineers, economists, so very convergent research from UNC Chapel Hill, UC Davis, Cornell, UC Merced, and NC State. So the work focused a lot on the Central Valley of California, certainly one of the most productive agricultural areas in the US. One that's a major water user. How do they manage drought? Well, in the past, it's largely been through the use of groundwater, when surface water is scarce, through reductions in precip, dry conditions. That water has been made up historically largely through the pumping of groundwater. But using groundwater solely as your insurance policy, those days are coming to an end. We've seen significant depletion of the aquifers, limiting availability. We're also seeing the imposition of a new regulatory structure, the Sustainable Groundwater Management Act, that will limit access to groundwater in the future. So the agricultural community's got to start coming up with more sophisticated approaches. Now, drought definitely has a direct impact on agriculture, but there are indirect impacts as well through the power system, electric power system. Hydropower is about 15% of the generation portfolio in California. When you have a drought, hydropower production is reduced. It's almost invariably made up with natural gas-based generation, which is more expensive, which drives the price of electricity higher. Now, the price of electricity goes higher at exactly those times when the growers are pumping the most groundwater and incurring the greatest expense in terms of pumping costs. And so that provides a compounding risk that the growers have to be cognizant of. So there's, of course, lots of stakeholders that are at risk. The growers in the irrigation districts are groups that we spend a lot of time with, but this runs down the complete agricultural supply chain. Of course, electric power utilities and their customers as well. There's also a lot of interest amongst key policymakers these days on coming up with new approaches to limiting the impacts of hydrologic variability. The idea that climate change, of course, is going to bring more of it. So I'm just going to focus on two groups for quick examples, the growers and the irrigation districts. So, of course, the growers have to make all sorts of decisions under uncertainty. An example would be whether or not to plant an almond orchard. This involves a big upfront investment that the farmer then hopes to pay off over time. Water availability is an uncertainty that they have to face. It's one that trickles down into uncertainty in costs and revenues that are going to have a big impact on farmers' decision making. So you can think about it in terms of discounted cash flow. If we're thinking about revenues, of course, the price of crops, the price of almonds in this case, is going to have a big impact. But when you think about costs, water plays a large role. Lots of variability in the availability of water. In those years where there's not enough available, it's very likely that the farmer is going to need to go out onto the water market and purchase supplemental supplies at very high prices, as you'd expect during drought. Alternatively, they might turn to groundwater, but as we've described, that involves some big financial costs as well, and imposes some additional risk. So in addition to the farmers themselves, there are the irrigation districts that provide all of the water delivery infrastructure that most of the Western US irrigators depend on. Now they finance this infrastructure and then they pay off this debt with revenue from water sales. But of course, with drought, especially the increased prevalence of drought in the Western US, these water sales have been down. And the groups that have started to take notice are groups like the credit ratings agencies that rate the credit worthiness of these organizations. They've started to impose hydrologic variability criteria, looking at, in this case, S&P talking about volatile and unpredictable water supplies as being a major source of enterprise risk. Now, if a district can't come up with ideas for how to mitigate that risk, it's going to lead to lower credit ratings, higher interest rates, and then invariably to higher costs for ag users. So what do groups like the credit ratings agencies and investors see? They see a picture that looks like this. An irrigation district that may have average revenues of $9 million or so is going to see its revenues essentially cut in half when available surface water is cut as a result of drought. This leads to a lot of challenges. What we find in the Central Valley is that there hasn't been a lot of rigorous efforts to try to characterize this risk or to come up with more sophisticated efforts to manage it. And so that's one of the things that we've tried to help out with. So this is a picture of what an irrigation district's risk might look like without any mitigation, without any efforts to manage it. Average revenues of about $9 million, a 20% chance of those revenues dropping to $7.5 million, and a 5% chance of them dropping almost in half to $4 or $4.5 million. So one of the ways that they can manage that is through a reserve fund. Most of these districts maintain some form of reserve fund, although it's not always carefully calibrated. In this case, you can see that the risk in the red there is significantly reduced, but at a substantial cost in terms of average revenues. You've got to set those aside. No longer can put those into regular use. So one of the things we've worked with the districts to do is to think about, well, what if we had a smaller reserve fund that was supplemented by something like index insurance, an insurance policy tied to hydrologic metrics. And in this case, what we see is you can improve the performance, both because the risk is about the same, even a little bit less, and you can do it at a lower cost than relying on a reserve fund alone. And so both the characterization of these risks and new strategies for managing these risks are something that's going to be an important factor as ag producers and those in the ag supply chain face questions from investors, from credit ratings agencies, groups like that. And it's going to be something that becomes more and more important as climate change begins to take hold. So last point I just want to make, I want to put in a plug for the idea that engineers, scientists, and economists should collaborate more. There are tremendous opportunities for convergent research, particularly in the area of agriculture. I think where we've got a real opportunity to come up with innovative solutions for a lot of the challenges that face the agricultural and food systems that we see right now. So with that, I'll finish up.